So we are looking at lesson 10, example problem 6. So we want to know what is our glider's speed if it's starting from rest after we push it for some particular distance. We need to go ahead and start by looking at what forces are acting on our glider. The first force that we have been dealing with is gravity. The next force is actually going to be the air cushioning our glider instead of the normal force because it's actually not sitting on the surface of the track. The last force we're looking at is the force of the push. Gravity and air both have the same problem. One, the gravity is going to be, not up, down, perpendicular to my displacement, so it can do no work there. Also, we are seeing no change in height, so we're not going to see any work happening there either. The next thing is the air. The air is taking place of our normal force in this particular case, so it's going to be up. Our displacement is across. As a result, force perpendicular to displacement, therefore our work is 0. The last one we're looking at here, the last force in this particular case, is going to be our push. Push is a muscle force. As a result, we know that muscle forces are non-conservative. All right, so we are going to see that this is the only force that is non-conservative. So this is going to be responsible for the work done by our dissipative forces. All right. A part of this is the conservation of energy law, and the fact that work done by our dissipative or non-conservative forces is equal to our change in energy. Because we're not seeing any change in height here and that kind of thing, our energy is only going to be made up of kinetic. So our initial energy is equal to our kinetic plus potential. But like I said, we have no change in height, so this actually goes away. So initial energy, 1/2 mvi squared. But remember, we are starting from rest. As a result, our initial velocity is 0 as well. So we are looking at the fact that we have an initial energy of 0 joules. All right, so now we can then look at our final energy. Our final energy is equal to, again, the 1/2 v squared plus our potential, which is 0. So we get a final energy of 1/2 mvf squared. So our work done by dissipative forces is equal to our final energy. So when we rearrange this, we see that our final speed is going to be equal to the square root of 2 times the work done by our dissipative forces divided by m. All right, so we're going to go ahead and find our work done by dissipative forces. That's over here. All right, we know the force of our push. It's given to us. It's our 5 newtons. We know the distance of our push. Our distance of our push is going to be our 0.2 meters, and our push is going to be in the same direction as our displacement because it's causing the displacement. So we're going to see the cosine of 0 degrees. As a result, we see a work done by dissipative forces equal to 1 joule. So now we can go ahead and plug all that in. All right, just to double check our math, we can go ahead and square root of 2 times 1 divided by 0.5. 2 times our work we just found, time divided by our mass, and we get a speed of 2.